All right, welcome back to Lag Demon Programming. I hope you're enjoying the video series. In the previous video, we talked about pointers and references, and I used a couple of for loops, and I had promised to explain them, but we kind of ran out of time. So I'm going to explain the for loop right now. A for loop in this standard format that I have here has three parts within these parentheses. The first part is a variable creation and initialization section. So all this is saying is that I'm creating a special variable integer I that has scope only within this for statement. It simply does not exist down here. If we said int a equals I, we get a red squiggly saying that it's undefined. Sorry about that. That's my phone making noise. What this is saying is that this I is not in scope. The I exists up here. It only exists within the scope of this for loop, and a scope is what these squiggly braces are all about. This is a scope. And it says that things that happen within that scope simply don't exist outside the scope. The second part of this is a condition. Oh, and by the way, you can define multiple here, comma separated. I can say int j also equals 0, and now my scope within this for loop has two variables, an I and a j. But we don't need a j, but that is a legitimate way to do that. You can create multiple variables. This is a single expression that's a Boolean expression that returns true or false. And it's very typical to just, in a for loop, determine that, in this kind of for loop, to determine that I is less than some final value. That terminates the loop when this returns false. So when I becomes equal to length, this becomes false, and this loop stops running. This section is the post operation that is performed at the end of the loop. So after each iteration of this loop, the last statement in that for loop is executed. In this case, we say I++. It doesn't make any difference if you say ++I or I++. We'll get into the idea of pre-increment operators, post increment operators, and the decrement operators and such in another video. For now, if we just say I++, that says increment I, and that is executed at the end of the for loop after the for loop is run. So there's what it would look like if it was a ++ increment operator. This doesn't make any difference. It'll still run at the end of the for loop and then check the condition. So you can almost think of this as it runs everything in between the two braces of the for loop. Then it runs the very last statement at the end. Then it checks the condition in the middle. And if the condition is still true, it continues to run. And this gets into the old saying that people keep saying that software developers count from 0. And I will tell you that this is an untrue statement. We count from 1 like everybody else. We index from 0 because of this operation right here. Our first address is the address that this is pointed to. That's our first element address. If we add 0 to that, we still have that first address. And then if we add 1 to it, we have the next one. And we add 2, we have the next one. That's called indexing, and it's pointer arithmetic. It's the only place in which we count from 0. We're not really counting, though. We're indexing from 0. So you can look at it this way. It's a way of relative addressing. If I tell you to turn left on my street and I'm the third house from the end, you would count house 1, house 2, house 3. Great. That's counting from 1. If, on the other hand, I said, well, the house on the end is at address 40, on my street, and that my address is that plus 2. Well, the address at the end of the street is that address plus 0. The next house is address plus 1. And the next house after that is address plus 2. That's the difference between indexing and counting. If we're taking an address and having to add numbers to it, and the first address in that is a legitimate thing, our index has to begin at 0 because we're adding the index to the address each time. Now, it's, as I said, it's not literally adding the number to the address because we're also multiplying this. The compiler's doing that for us by the size of our integer array. And we'll get into that when we deal with byte arrays or character arrays, where we might have to, take chunks and do the multiplication ourselves. But this is really just an index, and it's indexing along. So that's the basics of how a for loop works, and that's the difference between indexing and counting. And we count from 1 like everybody else. We just index from 0. So enough of that. So we have that. I'm going to save all this, and I'm going to close this file, and we're going to create another file, another source file here. Oh, actually, what I'm going to do is open that back up, and I'm going to do a little trick here. We have our main function here. I'm going to change the name of this main function to test1. And I'm going to add another source file. And this is just a little organizational trick I do when I want to deal with multiple ways of doing things. It's going to be a CPP file. I'm going to call this one main.cpp. And I'm going to show you a little trick here. So we can have int main return 0. I can type. Now, I want to be able to talk to test. I want to be able to call it, but it's in a different source file. It's in this source file, and I'm now in main, and it doesn't have a header file. So this is what we call a prototype. I'm going to come over here to int test1. I'm going to copy this. I'm going to come over here to main. I'm going to put it right up here. I'm just going to put a semicolon at the end of it. All right. This is a prototype of a function, and it says my function is called test1, and it resides, it doesn't have an implementation with it. There's no parentheses after it or anything, so the compiler recognizes this as a prototype, and it says I can call it, so I can call test1 from here, and when it goes to linking the program together, the compiler knows how to tell the linker that this test1 is actually over here. It's this test1, and it links it together. And since we have a new main function in here, this is now our entry point. It should call this. So I'm going to put a little cout here. We do have to include IOStream. And I'm going to say standard : cout starting standard : end L. Okay, and then we're going to call test1, and test1 should run. So what we should see is this printed here within this function. This should call this function. It knows about it because of the prototype, and the linker will cause it to link to this other one. When this compiles these source files, these main and so forth, it's going to compile them down to an object file, and then the linker's got to link those two object files together. And our project here in Visual Studio should do that for us. In another operating system such as Unix, where we might be working with make files, we might have to set that up ourselves, although there's a way to do that with some other tools in Unix, in Linux rather. We'll just talk about Linux. I use Ubuntu Linux, and we may do some stuff in that at some point in time with C++, because it's a different environment and it might be interesting to do. So let's run this now and see what happens. We should basically get the same program running, but it's got this starting at the top, and then it definitely called our main over there because it did all this as well. So that's what a function prototype is, and this is what, if you're just working with functions like these, in fact, we could prototype all of these over there, but that gets to be really, really annoying. If we had to write the prototypes to all the programs or all the functions that we want to call in every CPP file, we would be doing a lot of typing that's unnecessary. So in reality, what we want is a header file. And so this is going to be our first introduction to a very simple header file, and I'm going to show you some special techniques for that. So let's go up here to header files, and we'll add a new item, and it's going to be a header file, and we're going to call this CPP underscore tutorial underscore 1.h, and we'll add that. Now, okay, pragmas. All right, not all compilers understand these. Okay, at one time this was purely a Microsoft thing. I do believe that Pragma Once is now accepted by GCC and a few others and compilers, but I don't like it. I just, call me old-fashioned. We're going to do it the old-fashioned way. Rather than using Pragma Once, we're going to use macros. And it's a very simple macro, and it's very common, and it's extremely portable. Virtually every C++ compiler will understand this. The compiler directive we're going to use first. Compiler directives, by the way, always start with a pound, and these directives are used by they're preprocessor directives. They always start with a pound, and the first one we're going to use is if and def. Now I'm going to type in a couple of underscores, and I'm going to go CPP underscore tutorial underscore 1 underscore h. And I'm going to go pound define, and I will explain this when I'm done typing. And then I'm going to come down here and put pound endif, and I'm going to put a comment, and I'll tell you a little bit about comments. This slash here is a line comment. There's other kinds of comments. What does this do? This asks if this is not defined. If it's not defined, this if condition is going to allow everything between here to be included. If it is defined, it's not going to include it. Well, as soon as it runs, the first thing it does is define this. It's now defined. So if this happens to get included twice, it'll only actually get included once because of this. This is the equivalent of that Pragma Once directive. The Pragma Once directive says only include this header file once. If you see it a second time in the same stream of includes, don't include it. But like I said, I'm not convinced that it's highly portable, and I like to write as portable a code as possible. And one of the main features of C++ is its high degree of portability when it's written to be portable. If you use stuff, for instance, in Windows, if you use Windows API calls, you're not going to be portable because it's got to have the Windows API to run, and it's got to run on Windows. We're writing code right now that is not Windows API dependent, so we might get to doing something like that in the future, but we're not doing it right now. And so in this header file, I'm going to go over here. I'm going to get this prototype. I'm going to take it out of there. I'm just going to put it in this header file. Okay. Now it's in the header file. And in main, I'm going to include that header file. I'm going to say include. This time I'm going to use quotes. and you see it recognizes it right there. There's my header file, and this program still works. And now any of these prototypes I put in here can be placed in. In fact, what I'm going to do now is I'm going to just go ahead and grab all these functions, go over here to my header file, place them in, except I'm going to take the function body out. That was just an easy way to copy them, because we don't want the definition in here. These are just prototypes. It says what the function signature is and not what the actual function is. All those are now in the header file, and they're being included over here. I can run test1, which runs the test we have, but I can also do int a equals add 1 comma 2, and I can do standard colon 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 c out from a from standard end out. All right, and if we run this, should be perfectly okay with that. Starting 3, it ran my add function. So what we've done now is we've combined all those functions we created into this header file as prototypes, and we should put comments in here explaining them. You can use documentation comments, which work like this. If you're using Doxygen or something similar, probably have documentation comments. Add to numbers, and this can generate your documentation. So whenever you see these asterisks, or sometimes you'll see this, that's also a documentation comment. Various programs can be used to extract those comments and build API documentation and so forth, but we're not going to worry about that right now. I may do a tutorial on Doxygen at some point in time along this, because documentation is an important thing to understand. So that's the fundamental use of a header file. It's a place for prototypes and defines and macros and type defs and even class declarations. And we're going to get to classes fairly soon here, but I want to cover a couple other topics first. We're about 18 minutes into this one here, so one last topic I'm going to cover. We talked briefly in the very first video about this idea of a type def. It's an important and useful way of doing things. Basically, it's a way of creating an alias for a particular type. The C++ standard library has a variety of types. And by the way, I should probably tell you about one of the best C++ references out here. This is called C++reference.com. I go to this often, and I've already pulled up here a particular reference which has a bunch of defined types and macro constants and so forth. And these things are in various header files for different reasons. These particular ones here, the defined integer types, are in this C standard int file. These are also in C standard int. Let's see if there's anything else. Yeah, I think these are all pretty much in C standard int. And so I want to talk a little bit about typedef. If you go to cppreference.com or just type in CPP reference into Google, you should find these pages. There's tons and tons of material on here about C++, and it's very up to date. And believe me, nobody, even Bjarne Stroustrup, doesn't know in his head probably everything about C++ and uses references. We all do. No matter how long you've been doing it, nobody can remember everything that goes on. You have to have a reference. So we're going to put this include statement in here for this standard def, and I'm going to do a type def up here. There's quite a few interesting things. there is this particular thing called uint8t. This is an unsigned integer t. Writing these things out, especially for something like an unsigned integer, an unsigned 8-bit number, is typically called a byte. And so we can use typedef for this and define it as byte. And now, so in the C++ standard, instead of using terms like byte, which it's something everybody's familiar with, the term byte is very commonly used, but it doesn't mean precisely what most people think it means. Most people think byte means an 8-bit number. In reality, the term byte refers to the smallest unit of a particular platform. Because most of the Intel and AMD based platforms, that smallest unit is an 8-bit value, the term byte has become synonymous with an 8-bit value. But in reality, there are platforms out there where the smallest possible unit is 16 bits. And there might be another one with 32 bits as the smallest unit. There are some embedded processors used in certain specialty applications that have weird bit sizes, like 24 bits or even 12-bit. And on that platform, a byte is that smallest unit. So it doesn't always necessarily mean 8 bits. But we're in the Intel, AMD world. I like the term byte. I don't like typing uint8_t all the time, so I typedef it or alias it to the word byte. And that typedef can be used for a lot of different things. There are libraries that we will be working in here, and I'll include one right now, and I'll show you a little bit about how it works, called list. List is it's implemented. It could be implemented any of a number of ways. It may very well be a linked list of some kind. It could be an array or whatever underneath there they're handling it, but it has certain behaviors with it. And lists are in fact templates, and we're going to talk about templates, creating them at some point in time. But right now I want to talk about using templates a little bit, because things like lists and vectors and so forth are very, very powerful and useful tools in C++ programming. We will use them extensively, and even in Unreal we will use some template types. So if we know that we're going to extensively use a list of strings, let's also include the string. If we want to use a lot of lists of strings, to use a list of strings, let me go back over here to main. I've included these in this header file because we're going to do some typedefs here. But by including them in that header file, by the way, since I'm including that, they're also included here in main. So let's define, let's see what a list would look like. Let's type in standard : list standard : string my list equals oops, do this. Okay, that was a fair amount of typing. What I've done here is gone out, reached out and grabbed this list type, which is a template type. And I've told it to use string as its element for each list item. Each list item has to be a string type, which is a type within the standard library. And that's that header file that we included over here. we could actually include them just in the main program, but they're already included up there. Let's make sure this runs and that it's created correctly. Okay, it does. Now, we can do a lot of interesting things with list. In fact, we can use iterators. There's a couple of different ways of doing iterators in C++, and of course it depends on the version. I'm using a relatively modern C++ compiler, so we can do a shortcut, but I'm going to show you the long way at some point. Well, we could actually we could check this out now. Anyway, type defs could allow me to create another type out of this whole thing, so I wouldn't have to type standard : list, standard : string all the time. I could type def that and eliminate a lot of that typing. So we could do something like over here in this header file, we could do a type def of standard : list, standard string as string list. And now back here in main, we've got that one. We could just do string list other list equals this is a list of strings. And both of those are perfectly valid. This is a lot less typing than all of that. So that's one of the main uses of typedef that I would recommend, but just make sure whatever you call it, it isn't something unreadable. This is str list. Most programmers would probably be able to recognize that as a string list. It could be worded better possibly, but it's a lot shorter than all of this and a lot easier to type. So that's one of the reasons for it. Let's talk a little bit about list and let's do something with it. Let's create a simple for loop first. We'll do it the modern way first. And the modern way is going to be, we're going to have a standard : string. Actually, we can use auto here, I think. So auto is a way of doing what's called type inference. It just says that whatever the type is on the right, I'm going to make this variable. We'll call it auto str. We're going to put a colon and we're going to put my list here. So this is a special form of the for statement that's used for iterators. There's an older fashioned way that we used to do this, and I'll show you that in a bit. Let me double check the time here. Yeah, we're at 29 minutes, so we'll do this real quick and then we'll have to end this video. But we can do standard cout from string from std : endl, and all this is doing is saying for every one of these elements in this list, in fact, if I did other list, would be that one. We can copy it real quick. We'll do this twice and we'll put other list down here just to show that they both work. There we go. A little quick copy pasting. Is going to go through this list. This for loop is going to run this once for every item in this list, and this list is made up of these strings, which are of this string type, which is all overloaded to work with cout and everything, so it works great. Strings are fantastic in C++. Let's run this and see what happens. And there it is. It says Bill Westlake Programming. This is a list of strings, and then it's starting in 3. And that's because we had the starting down here. So that's just a quickie how mainly I wanted to talk about typedef because we're going to use that a lot as well. Let's go back over here and look at it. We took this long string. We took a crazy variable name and turned it into something more commonly known. A unsigned integer 8-bit unsigned integer type is now a byte in our system, and we can use that. And the same thing with this. We took this long name, and believe me, when working with templates, you can end up putting together some pretty long template constructs, and type defing them down can be very, very useful so long as you use a very readable name. So that's it for this video. Thanks for watching. I hope you enjoyed it. If you liked it, hit that like button. If you really liked it, hit that subscribe button. And if you want to get notifications when I upload videos, hit that notify button. Thanks, and I'll see you in the next video.